All right, now we're going to calculate the field due to an electric dipole. And what we're going to do here is really go through the math of it, which means there's going to be a little less of the physics behind what we're doing. I just want to go straight into the calculation. So what we want to do is we're going to prove, so this is what a dipole looks like up close. And I love how we draw the electric field this way, yet we define the electric dipole as going from negative to positive. This separation distance is d. This charge has a value minus q, this charge has a value plus q, and we actually define the dipole moment as q times the vector d that connects negative q to positive q. And then what we're actually out to prove mathematically is the idea simply that the electric field due to a dipole is given by the following formula. E equals 1 over 2 pi epsilon naught p over z cubed. And the idea is I'll actually draw a little dipole here with a minus and a plus. That was really bad. Let me shrink it down. With a little minus, with a little plus there, and a little minus here. And then here's our point. And what we're basically saying is from the center of the dipole, and let's remember this is the dipole moment P, this is how you calculate the electric field. So to do that, what I'm going to do is I'm going to label, and then we're going to do a little bit of an expansion. We did this one in class, and I talked about the rationale behind why we're doing what we're doing. Here, we're just going to straight up do the calculation. So I'm just going to put a negative charge right here at the bottom of this little line segment. And then I'll put a positive charge up here. And this is like an SAT problem. Distances are not to scale. And then here's a point at point Z. Okay. And we're going to put our origin right here. And so the distance here is d. And just to be absolutely clear, so this is our origin, I'll just move that there, because I want to make the point that this little distance here is d over 2, and this little distance here is d over 2. And here's what we're going to do. First, we're going to get the exact field. And we're subject to 2 approximations. So here's our process. First, let's get the exact field. Next, we make the approximation that d terms stay, and you'll see what I mean by that in a second, and d squared terms go to 0. And then what we'll do is we'll come up with a common denominator and simplify. And I do expect you to know how to do this process just to be safe, okay? So here we go, working with this. First we get the exact field. So step 1 is going to be us writing down the electric field from the positive and the negative charge. So that's going to be let me just write it as E from the dipole is going to be equal to E from the positive plus E from the negative charge. And now I'm just going to plug in my equations. So I have 1 over 4 pi epsilon naught Q, it's a positive charge, over whatever the positive distance is. We'll work that out in a second, squared, okay, plus, now the electric field from the negative charge, well, it's a negative charge, so it needs a negative sign. And I'm just going to do a little factoring here, r minus squared. And then here's the small point. The next thing to realize is that r positive actually equals, r for the positive charge is actually equal to z minus d over 2. And r from the negative charge is actually equal to z plus d over 2. And we're going to go ahead and make that substitution right now. So E ends up being equal to 1 over 4 pi epsilon naught q over z minus d over 2 quantity squared. This comes from looking at the picture. My distance from my origin up to here is z, but I'm d over 2 short for the positive charge. And I have an extra d over 2 for the negative charge, so this will be minus q over z plus d over 2 quantity squared. And now what we're going to do is we're going to simplify, and we're going to drop out d squared terms and keep the d terms. So here's what we get. We get E equals, and I'm going to drop the vector notation here because we just want the size, 1 over 4 pi epsilon naught. So we'll have Q over. Now I'm just going to FOIL it out. Z squared minus dz. Careful, it's not 2dz. It's 2 on the bottom. So when you do the FOIL thing and you get 2d times z, there's a 2 on the bottom here that cancels that. Plus d squared minus q over z squared plus dz minus d squared over 4, and that should be over 4 right here. Now we follow that suggestion that d squared terms drop out, so this will go to 0, and this will go to 0. That's just condition number 2, right? Yeah. That's just from condition number 2. Now we're going to simplify a little bit further. We're going to get that E equals 1 over 4 pi epsilon naught q over z minus dz minus q over z plus dz. And now we're going to give this a common denominator. So I'm actually going to borrow a page out of Jalan's thinking. She did this really efficiently. So we got q z plus dz minus q z minus dz all over. And then we do and this is 1 over 4 pi epsilon naught here. I'm going to do the difference of squares, so this ends up being z squared minus d squared z squared. Sorry, this is z to the 4th. This should be a squared here and a squared here. Now we'll simplify further. We're going to end up getting E equals 1 over 4 pi epsilon naught q z minus, so I don't know why that's a negative sign there. That's just weird. Oh, that's supposed to be an equals sign right there. Now, so this is qz. I'm going to FOIL it out, plus q dz minus q z plus q dz all over z to the 4th, because this drops out from condition 2. A little bit of simplification here. What we're going to get is that the electric field is 1 over 4 pi epsilon naught 2qz times d all over z to the 4th. So finally, when we simplify this, we get the exact result that we wanted to prove above. 1 over 2 pi epsilon naught q times d all over z cubed. And that's the electric field due to a dipole. All right, so that's it for the dipole calculation. In the next calculation, we're actually going to do our first integral.